Okay, we're here to talk about torque. We want to first start by comparing torque to force. So pause the video and write down a simple third grade description of force and a simple third grade description of torque. So force is captured in a simple sense by the words push or pull. Force is a push or a pull, and in that sense torque is a twist or a twisting force. Okay, we have a wrench, and this black thing is a nut, and we want to loosen it, so we need to twist it. So we need a twisting force. And obviously a twisting force requires a force, but notice I put in 1, 2, 3, 4, 5, 6 different forces, and they're all the same. They're all 100 newtons. The vectors may not look exactly the same length. They should be. And they're in different positions and at different angles. So pause the video and ask yourself which of the 5 is going to give you the most twist, which of the 5 is going to give you the least twist, and then try and rank those in between. Just like make a guess. So pause the video and rank from 1 to 6 the strength of the torque, from the strongest torque to the weakest torque. Oops, you didn't pause the video. Pause the video and do it. Just joking. I don't know whether you paused the video or not. But anyway, you'll learn better if you interact with these videos. So notice that I picked 3 as the strongest. Why? Because we all kind of intuitively know that the further away you are from the axis of rotation, this is going to rotate around the center of that nut, the further away you are, any given equal force will give you more torque. So this has the biggest torque. And hopefully clearly you can see that a force here is not going to twist it, and a force here is not going to do any twisting. So not only does the placement of the force matter, but the angle matters. So there's 3 things, right, in a torque: force, the distance from the axis, and the angle at which it acts. So clearly 1 and 4 are 0. And then 5 and 6, so 5 should be more. But I'm not really sure because the angle's smaller, right? And as this angle goes to 0 degrees, the torque is going to be 0 no matter where the force is. And if the angle goes toward 90, so this is a bigger angle, but I still guess that 5 is bigger than 6. To figure out which one is bigger, you might have to calculate. So let's put this into the form of an equation. So here's an equation, which is our definition of torque. Notice we use this Greek kind of tau, because T gets used for other things. So torque, if you're in Physics 101, you don't need to worry about this first part. And if you're in Calc 1, then you might not see this till Calc 3, but you're seeing it now. So torque is a cross product of 2 vectors. This is something that you don't get to Calc 3, but watch what it is. We have 2 vectors that are crossed into each other. It means you multiply the first vector, the r vector, times the second vector, the f vector, times the sine of the angle between them. So anyway, this is our working equation. But I'm introducing this cross product notation to the people in calculus because it's an important vector calculus notation. So our definition for torque is Rf sine theta. So let's unravel that. The R, okay, by all means learn this. R is not a radius. Even though it sort of is a radius in some cases, but don't say R is a radius. R is the distance from the axis to the force. So here the distance to the force is 0, so the torque is 0. Here, as the distance gets bigger to the force, from the axis to the force, as that distance gets bigger, the torque is going to get bigger. That's why, in general, we like to be far away. F, of course, is just the applied force. More force will mean more torque. And theta, you can't just, if I ask you these, you can't just say, oh, theta is the angle. No, what angle? Oh, the angle of the force. Oh, how do you read it? You've got to say this whole thing. You've got to write this all out. Theta is the angle between the R and the F. So if we go here, notice I put the 45 degrees here because here's the R and here's the F. And here's the R and here's the F. So if I chose another angle, it wouldn't be the right angle. So those are the three things that contribute to torque. And so now we can use this equation. So take this equation, practice, and calculate all 6 torques that we ranked here. And we'll see which is bigger, 5 or 6. So pause the video and try to do those calculations for practice. Okay, I hope you did that. And this is what you should have gotten. Obvious torque 1 is 0 because R equals 0. And torque 4 equals 0 because theta equals 0 and the sine of 0 is 0. Right? I'm using this equation. RF sine theta, that's what you're using. Then we come to T3. The distance is 0.4 meters. The force is always 100, and it's 90 degrees, right? You can see it up here. 3 is 90 degrees to the wrench, but it's not so much the wrench, it's this R vector. And so we get 40 Newton meters. And notice the units, Newton meters, force times a length, but one thing that's confusing, a joule is also a Newton meter, but you can't write this as a joule. It's just different. So you have to leave it as a Newton meter. Okay, we go to 5. The figure's a little small here, but that's 30 centimeters out, so 0.3 meters, 100 newtons. And the angle's 30 degrees, so when I do that, I get 15 Newton meters. And then the force 6 is at 20 centimeters. So 0.2 meters times the same force times the sine of 45. Oh, it comes out to be 14.1 meters. So my guess was correct, but you see it was very, very close. So even though this is closer to the axis, the angle is bigger. So those two torques are give you almost the same amount of twisting force. Okay, here's another situation very similar to a couple problems in your assignment. We have a disk with an axis through the center. The radius of the disk is 50 centimeters. And once again, we're going to take 3 forces, all the same value, 100 newtons. And this one is at the edge in this direction. This one is acting on the edge in this direction. And this one's grabbing something in the middle of the disk, halfway between the middle and the edge, and pulling in this direction. So how much torque or twisting is each of those? We'll call it one. Whoops. We'll call this 1, 2, and 3. This is also 100 newtons. So calculate the torques for each of those. Pause the video and do that. Okay, here are the values you should have gotten. The first one, I put in a sine of 180 rather than 0 because the R vector is this way and the force is that way, so they're opposite. But anyway, either way, 0 or 180, the sine is 0. Obviously, this isn't going to twist the thing. Here I took the angle to be 90 degrees. Well, if I look at the figure, it looks more like maybe 100 degrees. But anyway, it's supposed to be 90 degrees. You would just put the angle in there. So 100 times the sine of 90 times 0.5 meters is 50 Newton meters. And here it's halfway, so the distance is 25 centimeters or 0.25 meters. The force is 100. And the angle's given, right? Because the R vector is in this direction. You got to be careful. If I gave you a different angle, it might not be the angle. But in this case, the R is in this direction, the F is in that direction, the angle is 50 degrees, so I take the sine of 50, and I get 19.2. So that's torque. There is one other thing, and that's how is torque related to motion. So if you let's start from what we know. How is force and motion related? So that's Newton's second law. So if we have two forces that are equal and opposite, the thing is balanced, it's in equilibrium, it doesn't move. But if we have an unbalanced force acting on an object, it causes it to accelerate. So force leads to a change in velocity, right? Let's write that down. So remembering back to earlier in the semester, an unbalanced force will lead to a change in velocity and acceleration. But the amount of acceleration you get is inversely proportional to the mass. And so mass we called inertia. And inertia is resistance to acceleration. So how about torque? What do you think torque and motion is going to be related to? Think about that for a minute, and then I'll be back. So here's our second torque equation. Just like force tends to change the velocity of something, leads to an acceleration proportional to the mass, so too a torque tends to give something an angular acceleration. It changes its angular velocity or its rotational velocity. Like we want to spin a wheel faster and faster, we apply a torque. But things have inertia, but it's not the mass, it's the rotational inertia. So this is called rotational inertia or moment of inertia, and it's the subject of the other video. So you're now ready to go to the other video. But notice we have two primary equations: the definition of torque, which tells us how to calculate it and what it is, and the relationship between torque and the rotational motion of a body. Okay.